So you said this is a step function, and I know it passes through these points. This is what it would look like. So this is the formula, this is the graph. And he said, all right, I got this new kind of function. It's awesome. It's called piecewise constant function. Solving things, I'm constantly using these piecewise constant functions to model things. I think that we should, reason that he was interested in these is he worked on telegraphs, worked on making sure that the signals flow. So the Heaviside function, named after Mr. Heaviside, is like the fundamental piecewise constant function. And the basic Heaviside step, this is the right function. H of x is equal to 1 if x is greater than 0, and 0 if x is less than or equal. That moment we flip the switch, it suddenly changes. When we look at a function like the Heaviside step function, now we need a graphical way. So let's look at how we would actually graph the Heaviside step function. I have 0 if x is less than or equal to 0, and 1 if x greater than 0. So if I do h of x equals 1, it gives me this constant function, but I want to restrict that and only have that hold if x is greater than 0. And then I'm going to define the second part of h of x to be 0 if x is less than or equal to 0. I want to make these be the same color, so I click hold on the signal and change the color. But this graph is somehow unsatisfying because it doesn't tell me what h of 0 should actually be. So I want to add points here, and I want to add a closed point at what the actual value should be, which would be 0, 0. Would that be the same color? And then to say that this 0, 1 is not the correct function value, we'll use an open circle. So let me add here 0, 1, but instead of having it be a closed circle, let's have it be an open circle. And so this is a good graph for this function. A person should be able to look at this and know that h of 0 is equal to 0. The closed circle is where you actually see the function value. The open circle is just a way of signifying that that is not the function value you're looking for. This distinction between open and closed circles becomes important when we're looking at the graph of a function and we want to evaluate. So just to look at this, we're going to look at some of these values. You'll see in the places where there are open and closed circles how we determine the function value by looking at the closed circle at a particular number. It's p of -5. What do you have? Everybody, undefined. There's no -5 on this graph, and there's no reason to assume that we have anything else. What is p of -4? So you look at the x being -4, you look at the y being +4. What about p of -3? Also 4, it did not change at all. At x equals -3, I still have y equals +4. What about p of -2? 4, man, this is the most boring function in the world. It just keeps being 4. What about p of -1? So I have this at x equals -1, and we have y equals 2. What about, all right, this is the tricky one. P of 0. I'm going to make it be large font. You said p of 0 is 5. Okay, how do you know it's not 0? How do you see that? Yeah, we have this open circle versus closed circle business. So you're absolutely right. The closed circle means that's where the function is. The closed circle is what we actually use to define the function value. If you see an open circle, that's like, well, we were on our way here, but we're not here. So this is not the function value. And so the open circle is a special kind of symbol to let you know that there is a sudden jump and that you should look somewhere else. So now what about p of 1 is 1? What about p of 2? Again, we have this open circle versus closed circle business, so we have to know where to look. Now, what about p of 3? 4. What about p of 4? 1. What about p of 5? All right. So you'll have a good sense of how these things behave when they jump around.